talk about some specification problems. We'll talk about the easy ones first, since we only have 12 minutes. Let's talk about omitted variables. What does it mean to you to suggest that there are some omitted variables?
Significant variables that didn't consider in your suggestion.
No, it means that you missed out some of what ought to be in your model. What were the assumptions that we had for our garden variety regression model?
Stationarity.
Oh, I haven't talked about stationarity yet. Who's telling me about stationarity? We said that the rank of x was k. We said that n was strictly greater than k. X is non-stochastic. The expected value of u given x is 0. The expected value of u transpose x is 0. What else did we say? I guess that about runs it. But when you consider the list, implicit in the list is that you got the model right. You knew what right-hand side variables belonged there. Is that true usually? No. We're often on a fishing expedition. We're hoping that we have a pretty good handle on what belonged there, and if we try enough combinations and permutations of the different variables that we collect, for which we collected data, eventually we'll get it right. Right? So one of the things that we should be interested in is whether or not we omitted relevant variables and what the consequence is. Do we do much violence to our model if we omit relevant variables? So if you forgot to put in household wealth in your consumption function, arguably that's an omitted relevant variable. So to get a grip on the consequence of omitting relevant variables, let's suppose that the true model has k explanatory variables, but somehow, for some reason, we missed one of them and we included only k-1 independent variables. So that the model to which we fit the data is the second line at the top of the screen. And what we're going to do is we're going to construct a variable, a matrix x, that's a partition matrix, which is comprised of two parts. One part we'll call x with a tilde, and the other part we'll call x, in which we've augmented x tilde by the column of observations on the kth independent variable. So x tilde is all the observations on the first k-1 variables, and x with no tilde on it has another column of data in it. If we incorrectly use x tilde to estimate the regression, the model parameters, then beta tilde is going to be x tilde transpose x tilde inverse x tilde transpose y. And as we've done before, we should ask the question about the expected value of our estimator and its variance, and so on and so forth. We want to know the properties of our estimator when we've omitted these relevant explanatory variables. So what we'll do is we'll substitute away from y by the truth. So we'll substitute away from y by the truth, and then we'll take expected values. So when we substitute away from y by the truth, we end up with a matrix P times the truth. So depending on what values are taken by the elements of P, our estimator may or may not be biased. So it behooves us to look a little bit more at P. So let's first take a look at this term, x tilde transpose x. Let's take a look at that term, x tilde transpose x. Remember, x is the augmented matrix. So we have x tilde times the part in square brackets, which is x tilde augmented by xk. And we can expand the product so that we can show that it's actually equal to x tilde transpose x tilde. There's the partition mark. X tilde transpose xk. All the matrices are conformable for multiplication, and then we'll put it back together. So now we have x tilde transpose x tilde inverse post-multiplied by this partition matrix. When you multiply through, the inverse cancels the part that's not inverted. So we end up with a new partition matrix, which has an identity matrix of order k-1. And to the right of the partition, it it has x tilde transpose x tilde inverse, x tilde transpose xk, first multiplied by the truth. Well, let's take a piece out. The dimension of xk is n by 1. The dimension of x tilde is n by k minus 1. What does that part look like? You ever seen anything like that before? Say it louder. Yeah, looks like a regression, an estimated regression coefficient. That's the coefficient vector that you would estimate if you were to regress xk on the other k minus 1 independent variables. So apparently, the bias that you introduce by leaving out a relevant variable is going to depend on the covariance between the one that you left out and the others that you put in, so that the expected value of beta tilde is going to be the truth plus a regression coefficient, the covariance between xk and the other independent variable, times the true coefficient of the variable that you left out. So your estimator, when you omit a relevant variable, is going to be biased. And if you suspect which is the variable that you left out, you can even talk about the direction of the bias. This, by the way, is a favorite exam question. I've never used it, but I've seen it on many other exams used by other people, where they say, we ran this regression, but we left this variable out, and these covariances appeared, and so what's the direction of the bias?
I guess that goes with the fact that we have a bunch of variables that are multicollinear. Then it's not going to probably leave one out because you're picking up these variables.
If your experimental design is well done, then your right-hand side variables are going to be orthogonal to one another, in which case there's no bias from omitting a relevant variable. So people in agricultural economics, for example, or agribusiness in general, because they can design their experiments so that the independent variables are orthogonal to one another, they have it made in the shade. It doesn't matter if they omit relevant variables, because they can construct the design so that everything is orthogonal. We don't have that advantage. But you're right, if things are highly correlated, then you introduce a lot more bias. And you can tell what direction it runs, positive or negative. The punchline at the very bottom is that if you include irrelevant variables, no harm, no foul. Because if a variable is irrelevant, its coefficient, more often than not, is going to turn out to be 0. The only cost to including irrelevant variables is a modest reduction in statistical efficiency.
What's the point of doing this? I mean, if you know afterwards, hindsight's always 20/20. You know, other than to be able to make a mean test question.
Other than what?
Other than to be able to make a mean test question. If you mix it with
The moral of the story, one of the morals of the story is that don't put too much faith in the model that you estimate. Because as smart as you might be, there are surely omitted variables. And so no matter how careful you work, you would be ill-advised to say, this is the right sign of this variable. You know, it's all about variables. Here's another reason why. What we're doing, in case you haven't caught on, is that we had a set of assumptions for the garden variety regression model, and we've slowly been going through and relaxing them and saying, what's the consequence? How important is that assumption? So it turns out that not knowing the correct model can be pretty important. It might not be, but we don't know. We're going to talk about these specification problems, omitted variable. We've done that functional form, non-nested hypotheses, dummies and splines, missing data, pathological diseases, heteroscedasticity, autocorrelation, multicollinearity. Yes.